Thus, we continue our lecture. This is our sixth lecture number six. We are still discussing regarding the ARM as a new language for ARM processor. Okay, now we are still looking at the second operand of immediate value. As we use the immediate value as the second operand. As we know that there is no single instruction which will load a 32-bit immediate. This is if you look at the format of ARM instruction set, it is a 32-bit. So it is not possible to load a 32-bit as an immediate constant into a register without performing a data load from a memory. Okay, so the other option is to load it from memory. So all ARM instructions are 32 bits long. As you know, that ARM instruction do not use the instruction string as a data. It didn't have another string to use it as a data. Because in sys they can use as instruction string as a data, but not in ARM. The data processing instruction format has 12 bits. If you look back at the data processing format, instruction format, for the second operand immediate value, 12 bit only available for the operand 2. So if you use all directly 12 bit, you can have a range from 0 until 4069. But instead, it used to store 8-bit constant, which giving a range from 0 to 255. This 8-bit can then be rotated right through an even numbers of position. Okay, you can write this 8-bit to the right on an even number, either 2, 0, 2, 4, 6 until 30, which if you perform this kind of operation, this gives a much larger range of constant that can be directly loaded through some constant will still need to be loaded from memory. Not all the constant can be 32-bit constant can be use this format. Okay, but at least if you use this format means that you only require one cycle to accomplish the to execute. Okay. Uh, these are the examples. Okay. If you have from 0 to 255, okay, and then you have uh, you can have, if you rotate it by 2, then you can have 256 to 60 until 1020 and continue. Okay. Okay, these are the examples. Okay, this can be loaded using, for example, okay, you can use such as this movement. So if you write move R0 number 0 40 26 means that you can have load the 40696 immediate constant immediate number. To make this easier, actually the assembler will convert to this form for us if simply given the required constant. For example, you can also write this number. Then actually this is the way that the assembly do. It will compile it for you. Actually, it convert it for you. Okay, the bitwise complement can also be formed using move not. Okay, move not. Okay, right, such as this. Actually, assemble as move not 0 0. Assemblies that we convert for you. If the required constant, for example, you put certain constant which cannot be generated, then an error will be reported. It will show the error. So if the error occur, means that that number cannot be counted, cannot be immediate, number cannot be used. So in that sense, you need to use other kind of way in order to look 32 constant. Okay, although the move and move not mechanism will load a large range of constant into a register, there will be sometimes this mechanism will not generate the required constant, the one that you want, you cannot generate it. So therefore, the assembler also provide a method which load any 32-bit constant. And this is the way how you can load 32-bit constant. Okay, load a bit with a numbers constant. If the constant be constructed using either move or move not, then this will be the instruction actually generated. This instruction. Otherwise, assembler will produce an LDR instruction with a PC relative address to read the constant from a intermediate pool. It will read from somewhere else. For example, here LDR 42 generate move L0 move R0. If the number is greater than, it will generate LDR, and then the program counter will be put offset to the where this mechanism actually always generate the best instruction for a given case. So it is recommended way of loading constant. The assembly will recommend which way is the best instruction to be used. Now we go for a multiplication instruction. The basic ARM provide two type of multiplication instruction. Okay, the first one is multiply. Okay, this is the syntax. You can put condition, and then the suffix has destination and two other operands. So if you construct such as this, mean that R relation is equal to Rm multiplied by Rs. Then we have the other multiplication where we call it multiply accumulate. Okay, it do also the addition for free. Is there only one single instruction, it do multiplication and addition. Okay, the syntax MLE, the output, then we have condition, we have a suffix S, RD, the destination, the first, second, third operand where uh, after executing it, the destination register will contain Rm multiplied by Rs plus Rn, plus with Rn, and all of this in a single instruction. So there will be a restriction to use this multiplication. First of all, the R, D, and R, M cannot be the same register. Your destination and the first operand cannot be the same register. It can be avoided by swapping RM and RS around. You can use RS. Okay, this work because multiplication is cumulative, cumulative. So if you want to use the same destination, then you swap R, the same register to RS. Okay, you also cannot use the program counter. The program counter is one of the register cannot be used in the application. Okay, this will pick up by the assembler if overlooked. The assembler will notify. If you use the PC, then it will notify. It is you cannot use the PC as the register inside the multiplication. Operand can be considered signed or unsigned. Okay? It's up to the user to interpret it correctly. It can be used as a sign or unsigned. Okay, in the multiplication implementation, the ARM makes use of the Booth algorithm to perform integer multiplication. Okay, what we mean by Booth algorithm? On the non-M ARM, this operates on 2 bits of RS at a time. Only 2 bits of RS at a time. For each pair of bits, it takes one cycle. Another one cycle plus one cycle to start with. However, when there are no ones left in RS, the multiplication will early terminate. If you don't have any more 1s in the RS, then it will terminate. Okay, for example, you multiply 18 and negative 1, where RD, the expression is RD, RM multiplied by RS. Okay, we have RM is 18, okay, and RS is negative 1, all 1. Okay, note compiler does not use early termination criteria to decide on which order to place the operand. Okay, if you look here, this multiplication will require 4 cycles if you do the other way around. While if you uh, do such as in the station, it will take 17 cycles. Yeah, so this is a way to select appropriate way in order to do the multiplication in order to reduce the time to execute the instruction. And we have also extended multiply instruction. Okay, this is the end variant encore, which contain extended multiplication hardware, which means this provide the three enhancement. The first one is the 8-bit, both algorithm is used. 8-bit algorithm is used. Multiplication is carried out faster in this in the first one, the first enhancement. Okay, multiplication is carried out fast. Maximum for standard instruction is now 5 cycles. Only 5 cycles maximum. Early termination method improved so that now completes multiplication when all remaining bit set contains first all zeros, okay, as with non and or all ones. Okay. Thus, the previous example would early terminate in 2 cycles in both cases. In the previous examples, 18 multiplied by -1. If you look uh, at the binary number 18 and -1, if you revise, revise change the location of Rm and Rs, you only require 2 cycles. Both cases. 64-bit result can now be produced from 232 bit operands, which is going to be higher accuracy. And pair of register used to store the result. You require two register in order to store the result. So if you use two register means that you are using 64 bit of results. Okay, this is a multiply long and multiply accumulate long. Okay, this is the instruction MULL which gives the destination. You have to register. Okay, you can multiply RM and S. Multiply accumulate long, which give the same destination register. RM multiply S plus the result of the destination register 64 bit. Okay, however, the full 64 bit of the result now at a lower precision multiply instruction simply throw top 32 bits away. You need to specify whether operands are signed or unsigned. Okay, this you need to specify the operand RM or RS. So therefore the syntax for a new instruction, okay, such as this, uh, where it is not generated by the compiler, okay, and actually unpredictable for non-ARM processor. Okay, this is just to put the actually in this register also in this instruction also you can use the PC counter. Okay, now we go for a load and store instruction. The ARM is a load and store architecture. What we mean by load and store architecture? Because it does not support memory to memory data processing operation. You don't have the memory to memory data processing operation. So what you do, you must move the data value into register before you use them. You need to put into register before you can use them. This might sound inefficient, but it is in practice means that when you do the practical one, it's look okay. The load data value, the load data values from memory into register, process the data in register using a number of data processing instructions which are not slowed down by memory access. You know, when you try to access the memory, you are required, since it depends on the speed of the memory as well, so you can also store the result from register out to the memory bank. It is the one that you are using if you cannot do the data processing instruction within memory to memory. So have three set of instructions which interact with the main memory. Okay, these are the serial register data transfer, you have load and store, and then you have a block data transfer, and then also you have a serial data swap. Okay, I will continue this in the next lecture.